topic of this video is evading antivirus and EDRs with direct and indirect syscalls. I will always take a theoretical and then a practical approach to topics that I talk about, and I hope this can help you out. The main goal is to create a portfolio and also share the knowledge that I have learned and give back to the cybersecurity community that has helped me get to where I'm at right now. We start with the introduction to the 132 API. The 132 API allows applications to interact with Windows, targeting the user mode interface to the core system functions like files, memory, processes, Windows access tokens, and more. Malware often requires the use of common functions from the 132 API to execute shellcode, such as virtual alloc, write virtual memory, create remote thread, or if you're injecting into another process, then you'll need open process. So here we see the usual flow of the 132 API call. A benign Windows program calls a function from kernel32.dlo. We'll take create file for an example. It gets forwarded to ntdlo, which we'll call ntCreateFile. The call is passed to ntdlo and prepares it for execution. Here is where the syscall transition occurs from user mode to kernel mode, and then the Windows kernel processes the request and returns the result. The system calls a technical instruction in the Windows operating system that allows temporary transition from user mode to kernel mode. When ntdlo calls a function from the nt API, the syscall number is passed to the Windows kernel. From here, the kernel function ki-systemcall64 is executed, which will look up the kernel routine address for the syscall number in the system service descriptor table, or the SSDT, to execute the routine. System service dispatch table, or SSDT, is an array of addresses to the kernel routines for 32-bit operating systems, or an array of relative offsets to the same routines for 64-bit operating systems. This assembly code example, we have a syscall stub, and we'll be using ntallocate virtual memory as the example. So 24 is a syscall number for ntallocate virtual memory, and all syscalls usually will follow this stub right here. The value of RCX gets moved into R10, the syscall number gets moved into the EAX register, and then we have the syscall instruction. Why is using the 132 API a problem? Using the 132 API directly is a problem because of user mode hooks that antiviruses and EDRs place. User mode API hooking gives EDRs the ability to dynamically inspect code executed in the context of Windows APIs or native APIs for potentially malicious content or behavior. EDRs, ironically, usually use inline hooking and inject the DLO. Is another technique that malware uses. It'll inject DLL into a user mode process address space to monitor 132 or NT API calls. By replacing the move opcode and the EAX syscall operands with the jump instruction, the hook will jump to the vendor's injected DLL for code inspection. Here you can see this visual representation. We have virtual alloc gets called from kernel32 or kernel base DLL, and then ntallocate virtual memory gets called. Then the DLL will inspect this function getting called, pass execution back to the function, and then move along the transition to user mode to kernel mode. So how do we use custom syscalls to evade antivirus and EDR? Instead of obtaining the required code in the context of native APIs for the transition from user mode to kernel mode via ntdlo, the required content, the syscall stub, the native function is implemented directly in the assembly. This prevents code executed in the context of native APIs, which are hooked, from being redirected to the EDR's DLL and analyzed by the EDR. So here's an example of a direct syscall. As you can see, we completely avoid kernel 32 and ntdll and implement syscall stub directly in our executable. The transition to user mode to kernel mode happens directly in our application and then follows the usual kernel functions. Attackers use direct syscalls to avoid going through user mode hooks because it allows an attacker to execute a syscall without going through the Windows and native API. The attacker implements the syscall stub in its own application. For example, the WNT allocate virtual memory holds the syscall number for NT allocate virtual memory. Syscall numbers do vary between Windows versions, which is why projects like Hellsgate were created at a very high level. Hellsgate will get the PEB or process environment block of the current process, parse the P file format to dynamically retrieve the address of the NT API functions needed, carve out the syscall number, and store it for use in a custom assembly function. One thing to note here is that syscall instruction is implemented directly in our syscall stub. I have this resource here of the original Hellsgate white paper explaining how they had figured out a way to dynamically retrieve addresses of the NT API functions. There are some disadvantages of using direct syscalls. Direct syscalls may no longer be sufficient at this point of time to evade EDRs. The reason for this is that EDRs more and more are using kernel callbacks, which can be used to determine the memory area from which the syscall statement and the return statement are executed, or to which memory area the return statement points to. For example, if the return statement is executed outside the memory area of NTDLL, this is abnormal behavior and can be an indicator of compromise. To eliminate this IOC, we can use indirect syscalls instead of direct syscalls. In essence, direct syscalls can be seen as a practical and logical evolution of direct syscalls. Specifically, they allow critical operations such as syscall statements, the return statement, to be executed in the memory of NTDLL, rather than in the memory of the executable being used for execution. This approach is more in line with standard operating behavior, therefore seen as a more sophisticated technique. If we see this diagram here, we can see our executable doesn't completely implement the syscall instruction in our code, but it will point it to creates file address of the syscall instruction, and this can seem more benign to EDRs and antiviruses because it mimics the usual flow as close as possible. Here's a comparison of the two, indirect syscalls and direct syscalls. The main thing here is to notice the syscall instruction getting implemented directly in this assembly code. And then here, the Q syscall ret variable holds the address of the syscall instruction for NT-open process in NTDLL instead of the syscall and the return instruction getting executed in our executable or DLL's address space. It gets executed inside of NTDLL, which is normal behavior. And now I will show a demo of a debugger running for direct and indirect syscalls, giving you a better understanding of how this works. Also, a demo of me evading Windows Defender antivirus. I will start by presenting direct syscalls. The majority of this HD indirect code comes from Syscalls, which I do have an existing project up on GitHub. If you want to check that out, I'll leave a link in the description. So we will mainly be going over the assembly code here. Sys NT-open process is using direct syscalls. We have the usual syscall stub here. Move the value of RCX into R10. The syscall number that we retrieve dynamically into the EAX register. N3 sets a breakpoint here before the syscall instruction, and then the syscall instruction, and then the return. All of these other functions do use indirect syscalls, which I will show later. Gonna hit the breakpoints. The main thing to notice here is the instruction pointer. And you can see right here HG indirect, and then this address right here which is in our executables address space and not ntdll. Now we will see indirect syscalls in action under x64dbg. So we will set a breakpoint inside ntdll for the ntopenProcess function. Set a breakpoint at the sysconstruct, like it's already enabled. But notice this address here. This is the same address that we found during our debugging in Visual Studio Code. This line of code right here. So we'll go ahead and run this. So we hit this breakpoint right here. And then as expected, this jump instruction jumps to the syscall instruction here found inside of ntdll. And look at the RIB register. We see ntdll and then the address that we see right here. And then RSP. Well, if we follow this in the stack, this will be what we return to in this ret instruction right here. You can step into this. And then we see this address that we have right here, which is the return address.